Hey everybody, welcome back to Chem 103 lecture. We are in Chapter 7. In Chapter 6 we talked about the language of chemistry where we did naming and writing chemical formulas. In Chapter 7 we're going to talk about the types of chemical reactions, learn how to write chemical reactions in words, and how to balance chemical reactions. If you had trouble with naming and writing chemical formulas, you should definitely revisit Chapter 6 before moving on to Chapter 7. You need to be able to recognize formulas, those polyatomic anions, all the things from Chapter 6 you need for Chapter 7. So please, 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 I urge you, if Chapter 6 was a struggle, you have some issues, reach out, get that help, because you need it for Chapter 7. Let's get to it. I'm going to remind you of the chemical and physical changes that we talked about in Chapter 3. In a physical change, the composition of the substance remains constant. So you're not doing any kind of chemistry, no reactions. We're talking about a change in state or a change in shape. Examples are melting ice, boiling water. With a chemical change, the chemical composition changes. We're talking about a chemical reaction. You're taking some reactant or reactants, putting them together in a new way, and forming a new substance. There are 4 observations that indicate a chemical reaction is taking place. You don't have to see all 4 for a chemical reaction to take place, but these are 4 observations that can clue you in that you are watching a chemical reaction. The first is that a gas is produced. And you might see that in many different ways, like a little bit of fizzing, lots of bubbles. It could be anywhere in that range. In the image to the right, you see the release of hydrogen gas. That's all these bubbles here. It's kind of violent. And that's magnesium metal mixing with an acid. You see all that bubbling going on, and then you don't see any more metal. The magnesium, poof, seems to just disappear. Now it doesn't disappear. You've just created a new solution, and you've liberated hydrogen gas. The second piece of evidence you might observe is an insoluble solid being produced. That insoluble solid is called a precipitate. If you can take 2 aqueous solutions, which just means you've got some stuff dissolved in water, right? If we take 2 different aqueous solutions and mix them together, all of a sudden you have a solid substance forming and starting to settle to the bottom. That's chemistry right there. And you formed a new compound that is no longer soluble in water, and so it is falling out of solution. You're forming a precipitate. In the image here, we have a yellow precipitate forming. And that leads us to the third piece of evidence you might observe. That's a permanent color change. Oftentimes you'll see some kind of a color change. You may see a color change in addition to observing a gas forming or a solid forming. A change in color means that you've made a new substance. Some of the metals, especially the transition metals, have very pretty colors. Cobalt can be a nice pink. Copper can be a nice green. So it's very colorful. Chemistry can be very colorful. The fourth piece of evidence is an energy change. And what that means is that you can notice that a reaction vessel is getting hot or cold to the touch. A reaction that releases heat is an exothermic reaction. And you'll need to know these terms. So exothermic releases heat. Endothermic absorbs heat. What that means for observation, if there's an exothermic reaction, your flask or your reaction vessel gets hot. If you have an endothermic reaction, your flask gets cold. Those are observations that you can make. Now, I wouldn't necessarily recommend putting your hands around a flask while you're doing some kind of chemical reaction and saying, oh, wow, that's getting hot, because you can get burned. Okay, but that is absolutely something that you can tell by putting a thermometer in there, and you can see the temperature increasing or decreasing of your solution. Here's some practice that you can use to figure out whether or not there's a chemical reaction or not. It's like a game show, right? We'll do more of these in class too. So I'm going to go over these three, but we'll do some in class together. Mixing baking soda and vinegar results in formation of bubbles. Chemical reaction or not? It's a chemical reaction, which I will abbreviate CR. It's a lot of writing, y'all. The formation of bubbles tells you that you're making a gas. And the baking soda vinegar thing, that's how you make one of those volcanoes. If you've never done it, you should. Baking soda, vinegar, a little bit of dish detergent, maybe some red food coloring if you're feeling a little bit creative. A little bit of water to kind of thin it down a little bit, because that dish detergent can be rather viscous. You mix it all together and, you make lava, yay. It's a fun thing to do with kids. Or if you're, you've got an inner child, it's fun to do for yourself too. Moving on. Cooling carbon dioxide results in the formation of dry ice. All we're doing is cooling here. That's a change in state, which means it's a physical change, so it's not a chemical reaction. Nah. Two liquids are combined in a green precipitate forms. We're forming something that's a different color, and it's a solid. We started with two liquids. That's definitely a chemical reaction. So this should be a little bit of a refresher, again, from Chapter 3. If it's not, go back to Chapter 3, do some practice, and then come on back to Chapter 7. Now we're jumping into writing chemical equations in words. We talked about the evidence for observing a chemical reaction. Now we need to learn some more of the language and how to put the language and the verbs together. So the language from Chapter 6, a little bit of verbiage from Chapter 7, and we can write a chemical equation in words. First thing you need to do is name all of these compounds. So let's take a second and do that. This will be a little bit of a review of Chapter 6, and it'll let you know if you need to review Chapter 6. Our first compound is some kind of an acid, which you can tell because of the AQ and that H in front. C2H3O2 is acetate, the acetate ion. When it's ATE, you turn it to IC and write acid. So that's acetic acid. NaHCO3. HCO3 is another polyatomic ion. It's bicarbonate or hydrogen carbonate. Those are our two reactants. The reactants are always on the left-hand side of the arrow. This arrow means yields. So we're taking our reactants and we're making something else, and that something else we call the products, which are always on the right-hand side of the arrow. Now let's name our products. We see that acetate ion again, so we name it sodium acetate. H2O, we could name it using the BMC rules for binary molecular compounds. I'll do that. Dihydrogen monoxide. But we could also just call it water. It's liquid water. And our last product is CO2, which is a binary molecular compound. So we use the same rules that we did for naming water. We've only got one carbon here, so you just write the carbon. Di for 2. Oxide to show that it's oxygen and it's the second element. Okay, now we've named all of our compounds. Let's take note of what the states of matter are. So that's what's in parentheses here. AQ, S, L, G. Those are all states of matter. When we're writing a chemical equation in words, we have to put all of the information that you would normally get in the equation into our little paragraph. So the acetic acid is aqueous. The sodium bicarbonate is a solid. Sodium acetate, aqueous. H2O, aka water, that's a liquid. CO2, the carbon dioxide, is a gas. When we're putting all this together, we have to mention all of these parts. We'll start with the reactants. Well, what do you do when you're doing chemistry? You mix things together, right? So you can use verbs like, and I'll give you a list here: mix, combined. Those are words that you can use. We've got acetic acid. Oops. I usually like to start with writing the state of matter. So aqueous acetic acid and solid sodium bicarbonate are mixed to yield. Now we talk about the products that we make. We've got aqueous sodium acetate, we can just say water here because water is a liquid. That's our understanding of water. It is liquid H2O. And gaseous carbon dioxide. You could also say carbon dioxide gas here. Let's identify each of these parts. Our reactants come first. We just listed what they are. Then we did the arrow, the yields. Our mixed to yield. Our combined to yield, you could say, depending on what the reaction is, decomposes to yield. anything that describes what you do to get to the products. Then we have the products. And that's how you write a chemical equation in words. You have to name all of the compounds, make sure you include the states of matter, and then you hook them together with a phrase like are mixed to yield or combined to yield, decomposes to yield, which we'll talk about what a decomposition reaction is. But all of those verbs or turns of phrase are perfectly fine when you're connecting the reactants and the products. Just make sure you have some kind of verbiage there that says that you're making something. You could also say, instead of to yield, to produce. They're the same thing. So it's really up to you. You can be a little bit creative here about your word choice. As long as you're naming all the compounds properly, you're including the states of matter for each compound, you're good to go. Here are the symbols that you'll see in chemical equations. Now we saw a lot of them, but not all of them. The first one is the arrow, and that's the produces, yields, gives. It separates the reactants from the products. So it's always in the middle. The plus sign, that means reacts with, added to, plus. It separates the reactants and the products when you've got two or more. This little triangle over the yield sign, that means heat. So you have to add heat. Likewise, if you see a metal like iron or platinum or palladium over top of the arrow, that means that those metals are a catalyst for the reaction. If you see Nr on the product side, then that means there's no reaction. So you might mix two solutions and you don't see any fizzing. There's no color change, no heat increase or decrease, right? Just nothing. You just mix them together. That's not a reaction, so you put Nr. When we get further along in talking about the types of chemical reactions, you'll see where this can come into play. Finally, we have all of our states of matter: solid, liquid, gas, aqueous. And remember that aqueous just means a substance dissolved in water. This chart is a good one if you need to kind of quickly glance and say, okay, what do these symbols mean? Or let me make sure I'm spelling things right when it comes to the states of matter, anything like that. So I'd recommend putting this in your notebook. You will not get it on the exam, so you'll need to know all of these. But put it in your notebook for your reference. Here's another one. We're going to write a chemical equation in words. I recommend pausing here, giving it a shot in your notebook, and then catch up with me and see how you do. So this equation, it's a specific type of reaction that we're going to talk about. So I'm going to use a verb here that we haven't talked about yet. You've seen it, but we haven't talked about what it means. We'll talk about it shortly. As always, I'm going to start by naming all of my compounds. The first one is a ternary ionic compound because we have this carbonate ion. aluminum carbonate, Al2O3 is aluminum oxide. Remember, aluminum is a group 3 metal. It is not a transition metal, so you do not need to put anything about aluminum's charge. It's +3 because it's group 3A. Don't need to tell the world that, because the world should know. Last but not least, we see carbon dioxide again. Now we put all our states of matter. We've got solid for the aluminum carbonate, solid again for the aluminum oxide, and gas for carbon dioxide. Reactants are on the left-hand side. We see the triangle here, so that means heat along with our yields. So we need to mention that heat, and then the products. There's only one reactant here, and that's the aluminum carbonate. And what it does with heat is it decomposes into multiple products. We're going to talk about decomposition reactions in just a few minutes here, but just stick with me. This is how you write it out. Aluminum carbonate, solid, or you could put the solid in front, doesn't matter. Decomposes with heat to yield, or produce or give, your choice. Solid aluminum oxide and carbon dioxide gas. Our reactants, well, we've only got one. That's the aluminum carbonate, and we said that it was a solid. Cool. Our yield sign, we had to mention something about heat too. And it decomposes with heat to yield our products. And we listed those, and we've got the states of matter. Always double check to make sure that you cover those small details, like the states of matter, whether or not something is heated or there's a catalyst. Those small things can be the difference between getting your homework questions right or wrong, or an exam question right or wrong. Even though this is not a difficult thing to do, it's very easy to overlook small details. So don't rush through it or say, I got it. Double check. It's kind of like, you know how to spell the word the, but sometimes you type it wrong. It's TEH. We know that's not what it's supposed to be. But it's easy to overlook it when you're rushing. Don't overlook the little details. Those little details are sometimes the difference between an A and a B, or passing and failing. Now we've got to go in the reverse. We've got to take a written description and write a chemical equation. So from chapter 6, what you'll need to do is be able to identify the compounds and write chemical formulas from the words. Let's break this down. Solid magnesium metal and oxygen gas are combined and heated to yield solid magnesium oxide. Well, let's identify our reactants. There they are. Are combined and heated to yield, that's our arrow, solid magnesium oxide. Those are our products. So when you see this description, immediately you should identify reactants, the products, and how they're linked, whether or not there's some heat, a catalyst, or anything like that. Then you go through and you write it out. So magnesium metal, that's Mg, and it's a solid. Oxygen gas, that's O2. We're going to talk about how you can know when you should write something like O2, because oxygen gas, you might think, oh, I should just write O and then a G. No. Oxygen is what's called a diatomic molecule. We'll talk about those in this chapter too. Now we hit our yields arrow, and it says that it's combined and heated to yield. So we have to have our triangle. The product is solid magnesium oxide. Now remember, magnesium oxide, that's a binary ionic compound, which means that the metal ion and the anion, when you add those charges up, they should be equal to 0. Magnesium is a group 2A metal, so its charge is 2+. Oxygen is group 6A. You subtract 8 from 6 to get the charge for that, and it's 2-. So when I put one of each of these ions together, I get an overall charge of 0. Don't forget to do that. What you're doing is chapter 6 with a little bit more to make a sentence. So don't forget all of that about how you take the words, the names of these compounds, and write it as a formula. All of those rules still apply. All that said, this is our answer. Make sure that you have your states of matter for each compound. If there's heat or catalyst, it's listed. That you have your arrow, plus signs where they're supposed to be. We'll do one more. Pause it, give it a shot yourself, and then join me and see how you do. We've got cadmium metal is added to aqueous cobalt 2 nitrate to produce aqueous cadmium nitrate and cobalt metal. Let's identify our reactants. We've got cadmium metal being added to aqueous cobalt 2 nitrate to produce, that's our arrow, aqueous cadmium nitrate and cobalt metal. Those are the products. Now we just write it out. Cadmium metal. When you see that it's something metal, that means it's a solid. Aqueous cobalt 2 nitrate. I'm not going to go into detail here about how I went from cobalt 2 nitrate, the words, to writing out the chemical formula. But if you can't make that jump, please go back to chapter 6 because you need it. I will probably say that again one more time before the end of this video, but it is critical that you understand the previous chapter for you to be successful in chapter 7. Okay. To produce, we put our yield sign. There's no heat, no catalyst, so we're good to go there. Aqueous cadmium nitrate. Cadmium is a transition metal, but it's an exception, so it only makes a 2+ ion, and that's it. cobalt metal. It's just solid metal. Make sure you've got all of your states of matter, that your formulas are correct. Double check those. Make sure you don't need any heat or any catalysts over your yield sign, and you should be good to go. There's our answer. So we've been writing these chemical reactions. We're writing descriptions. We're writing the reactions, the equations, with the formulas. We need to classify these reactions. There are 5 that we're going to cover. And along with these 5, we're going to be talking about some other related concepts. We've got combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and neutralization reactions. We're going to go over all of these, and in the live lecture, I'm going to help you make kind of a cheat sheet so you can have an idea of what each of these means. It'll help you study. So come to class. We'll start with combination reactions. You'll need to know all of these terms. So if you're a highlighter, if you're a, make flashcards, whatever it is, do that so you can learn these terms. You need to be able to classify reactions. We've got a combination reaction. You take simpler substances and you combine them into a more complex compound. The other term you might hear for these is synthesis reactions. Same thing. Here's an example. When you heat a metal with oxygen gas, you make metal oxide. So this is the generic reaction. You've got a solid metal, you add oxygen gas, you make metal oxide. The example is, let's say you've got magnesium, and then you heat it, that's what the triangle is, with oxygen. You make magnesium oxide. Notice how many reactants you have versus how many products. You've got 2 reactants. You've got 1 complex product. Sometimes you need heat for combination reactions. It's not a requirement. But in general, for a combination or synthesis reaction, you're taking 2 or more reactants and combining them to make 1 complex product. That is the key here. You can also take oxygen and a non-metal and produce a non-metal oxide. One example would be reacting sulfur with oxygen, and you produce sulfur dioxide gas. You've got 2 reactants coming together to make 1 product. That is the hallmark of a combination reaction. Many reactants, 1 product. Another combination reaction you can see is a metal plus a nonmetal, and they'll react to make an ionic compound. The example we have here is lithium reacting with bromine gas to produce lithium bromide. 2 reactants. They make 1 complex product. Now we've seen heat for all of these, but again, whether there's heat or not, it's still a combination reaction. The next type of reaction is a decomposition reaction. We've got a single complex compound that's broken down into simpler substances. Oftentimes, you need heat just to get things going. Here are a couple of examples. You heat mercury 2 oxide and it produces mercury metal and oxygen gas. One complex reactant, heat 2 simpler products. What this is essentially the reverse of a combination reaction. RXN is my abbreviation for reaction. The second example, we've got calcium carbonate decomposes to yield calcium oxide and carbon dioxide gas. Again, you see that triangle meaning heat. One complex reactant, heat, 2 simpler products. And what we mean by simpler is just there aren't as many elements in each compound. So we've got 3 elements in this complex reactant. We've got 2 elements in one product and 2 elements in the other. So those are simpler. Again, it's the reverse of a combination reaction. So if you can remember a combination reaction because it tells you what it is in the name, just remember that decomposition is the opposite. Before we can go to our next reaction type, got to tell you about an activity series. Okay. Metals can undergo single replacement reactions, which is the next type of reaction we're going to talk about. And what that means is that it displaces one metal from a compound or an aqueous solution. The metal that can do the displacing is more active than the metal that is replaced. So the activity that we're talking about in the activity series is the ability of a metal to compete in a replacement reaction. There's a relative activity series, and you'll be provided with this on your exam. This is the most active metal, lithium, all the way down to the least active metal. What you use this for is to determine whether a single replacement reaction will occur. You have 2 different metals in this reaction. Will one of them replace the other in a solution? So let's say that I have zinc and I have mercury. Which one is more active? I'll use red here. You find zinc, you find mercury. The one that comes first is the one that's the most active. That would be zinc. We'll do the second one in orange. We've got copper and tin. Here's copper. Here's tin. Tin comes first. So it is the most active metal in the pair. Last one, we've got lithium and iron. Well, lithium, we already said, is the most active metal. So anything up against lithium, lithium wins hands down. But for completion's sake, here is iron. Lithium is clearly before iron, so it would replace iron in a compound. That's how we use the activity series. This concept is what we need to talk about single replacement reactions. This is a reaction where a more active metal displaces another less active metal in a compound. This is our compound, copper 2 sulfate. It's aqueous. We then add some solid iron, and that's what this rod is here. This is solid iron. This pretty blue is the copper 2 sulfate. I told you chemistry is beautiful. Eventually what you'll see is copper being plated onto the iron. And that's what this kind of blow up is. So you see this brownish here. That's copper coming out of solution. The kind of metallic-y looking silver stuff, that's the iron. Iron is more active than copper. So if copper is in a solution, the iron will replace the copper in the solution. And that's what happened. So the copper becomes just solid metal, and the iron becomes a part of the solution. Let's do some practice problems. Will solid silver react with aqueous copper 2 nitrate? Well, in order for solid silver to react with copper 2 nitrate, that means that silver has to come before copper. So we can rewrite this question as, is silver more active than copper? Then you'd look at the activity series and find both of them. Here's silver, here's copper. Copper comes first, which means no, silver is not more active than copper. So it will not react with aqueous copper 2 nitrate. There's our answer. Let's do some more practice. We're going to do some fill in the blank, complete the single replacement reaction problems. The activity series is at the bottom. I'll walk through the first one with you, and then I would like it if you pause and try to do the second one. We've got zinc solid. We've got lead 2 nitrate, and it's aqueous. What this is asking is zinc more active than lead? The lead is in solution. If zinc is more active, i.e. it comes before lead on the activity series, then we'll see a reaction and we'll switch the ions. Let's find them. Here's zinc. Here's lead. Since zinc comes before lead, yes, zinc is more active. So that means you're going to swap these. you're going to have solid lead and aqueous zinc nitrate. Just so you can track where each of these metals goes. So we said yes, zinc is more active, so we switched them. The lead is the solid, it's a precipitate, and we have zinc nitrate. What if we reversed it? We've got solid lead and zinc nitrate. Now the question is lead more active than zinc? The answer to that question is no, because zinc comes first. So if you put a piece of solid lead into zinc nitrate, nothing's going to happen. That lead is just going to sit there. In that case, we write NR for no reaction. We'll do more practice like this in class, but the key is knowing what these reactions mean in terms of a question that you can use the activity series to answer. We can also have aqueous acid displacements, which are similar to single replacement reactions, but instead of a metal, you're replacing hydrogen. So you'll notice that in the activity series, there's that H in parentheses, that's for hydrogen. All the metals that precede that hydrogen in the activity series will react with acids, and those that come after don't. So an example of an active metal would be iron mixing with hydrochloric acid. You'll end up making iron 2 chloride and liberating hydrogen gas. If it's less active, then you have NR for no reaction. Same concept, only you're comparing hydrogen and a metal versus two metals. There are some metals that are so active that they can directly replace the hydrogen in water. So the first two groups on the periodic table, groups 1A and 2A, they're the alkali metals and the alkaline earth metals. They are very, very reactive. So if you take a small piece of sodium metal and you put it in the water, you will see a lot of violent bubbles form. It also gets really hot. It's a really cool thing to look up. Like, you can watch it on YouTube. Kind of dangerous to do, but very great for a demonstration. These metals are actually, like, if you have solid sodium, you don't just store it in open air because it's that reactive. It will react with the oxygen in the air. You actually have to store it in oil. So these are just some more examples of single replacement reactions. You can have an aqueous acid displacement. You can have an active metal mixed with water. Same thing. So we've covered combination reactions, decomposition reactions, single replacement reactions, and we also talked about the activity series along the way. That is 3 reaction types. We've got 2 more. Double replacement reactions. This is similar to the single replacement, only instead of you having one solid metal and then some kind of aqueous solution, you have 2 aqueous solutions. And when you mix those solutions, you form a precipitate. The ions switch. Notice where the barium is. It starts off with the chloride. So barium chloride. What that means is you've got barium 2 plus floating around, and you've got Cl minus floating around. When you add the potassium chromate, that means you've got some potassium floating around and some chromate ions floating around. That chromate is one of the polyatomic anions. When they're mixed together, the barium and the chromate get the opportunity to meet each other. And when they do, they say, oh, you know, let's fall out of solution. Let's be a little bit different. So you form a solid, and then you've still got the potassium ions and the chloride ions hanging out, floating around like, we like it better in the water. We're gonna stay in here. When you form this precipitate, that means that you have a double replacement reaction. If you don't form a precipitate and you just see aqueous, you don't have a reaction. So remember this. You've got to form that precipitate as a product. Now you might be wondering, how in the world do you figure out whether or not you're going to form a precipitate? Here's how. The solubility rules. This table will be provided for you for your exam, so do not memorize. However, it will be utterly useless if you don't practice how to use it. Let's talk about what's in this table. There are two parts to this table. The first one talks about things that are generally soluble in water. Okay, so that's 1 through 5. If you see any of these things, they're going to likely be soluble in water. Then we've got 6 through 10, which are insoluble in water. That red is angry, isn't it? That's why I used it. Insoluble, angry. So the first 5 rules, we're talking about things that are soluble. Alkali metals. So that first group 1. So group 1 metals. And things that have the ammonium ion. That's the NH4+. Any compound that you see with group 1A metals or NH4+, it is probably going to be soluble in water. Likewise, if it has acetate, nitrate, halides, sulfate, it's going to be soluble. Remember that a halide is equal to one of the halogens. So fluorine, chlorine, bromine, iodine. There are some exceptions. Those exceptions are insoluble. So if you see AgCl or Hg2Cl2, PbCl2, those are all insoluble because silver, mercury 1, and lead 2 do not like the halide ions. And they're like, look, come for me, bro, but we gonna fall out of solution together. Likewise, we have some exceptions with the sulfates. Strontium, barium, and lead 2 sulfate are also insoluble. So everything highlighted in red, insoluble. Now we're going to move on to the second part of the table. And this is, these things are usually insoluble, but there are some exceptions. Anytime you see carbonate, chromate, phosphate, it's very likely going to be insoluble. The only exceptions are Rule 1 exceptions, which means Group 1A metals and ammonium. All those are going to be soluble. Anything outside of that, not. Anything with the sulfide ion, going to be insoluble, except for these: calcium, strontium, barium, and of course the group 1A and ammonium. Same thing with hydroxides: calcium, strontium, barium, plus group 1A and ammonium. Those are soluble, everything else not. Well, this is great. Lots of rules, lots of stuff to kind of remember. Let's practice how to use it. The best way that you can use it is to remember this simple rule, and it'll get you through a lot. All group 1 metal ions and ammonium, nitrate, and acetate soluble in water. If you'd see something other than that, it is likely insoluble. Let's practice. We've got aqueous sodium chloride reacting with aqueous lithium nitrate. We have to figure out whether there's going to be a reaction or not. Just because we mix them together doesn't mean that there's going to be chemistry. Chemistry means you see a solid form, a gas produced, color change, heat. So let's see. If we have sodium chloride and lithium nitrate, then what we've got floating around is Na+, Cl-, Li+, and NO3-. We're going to swap our ions. So now we've got sodium nitrate and lithium chloride. Sodium nitrate. Well, sodium is a group 1A, right? And we've got nitrate. So that's going to be soluble. Okay. Group 1A, soluble. Lithium chloride. Lithium is group 1A. So it's also going to be soluble. That means it's aqueous. They're both aqueous solutions. So there's no reaction here. We did not form a precipitate of any kind. So that is not a double replacement reaction. You just mix two things. You may as well have put water in water, because nothing happened. Our last reaction type is a neutralization reaction. And be careful here, because these can look a little bit like the double replacement reactions, but they are different. A neutralization is the reaction of an acid and a base. An acid is going to have that hydrogen first, and then either a polyatomic ion or an anion. Our example here, we have sulfuric acid. Notice the sulfate. Notice the hydrogen in front, and it's aqueous. That is our acid. Bases we didn't talk about. With our base, you're going to see something that's got a hydroxide, by and large. There are other bases that don't have a hydroxide, but I'm not here to teach you about bases today. I'm here to teach you about the general neutralization reaction. So for our purposes, if you see OH plus a metal, then you've got a base. In our example, we've got potassium hydroxide, but it could be sodium hydroxide, it could be any hydroxide. When you mix those two together, you will always get water. Water will always be a product. You'll also create a salt. So think a ternary ionic complex or binary ionic complex. Those are called salts as well. This is a neutralization reaction. Notice there's no solids here. There can be, but you don't have to make a solid. And that's the difference with a neutralization reaction. You always make water, and some kind of ternary ionic compound or binary ionic compound, which can be aqueous or a solid. That's how you can tell the difference between double replacement and neutralization. It will come up, and when it does, hopefully you will remember this. Neutralization needs water. Here's some more practice. Are these compounds soluble or insoluble in water? I'd recommend pausing it here. Make sure you have that solubility rule sheet handy and try these out. Then the final question is double replacement or neutralization reaction, so that you can figure out the difference between the two. Let's start with practicing our solubility rules. We've got mercury 2 chloride, HgCl2. Well, the exception is mercury 1, which would be Hg2Cl2. So this one's soluble. Silver bromide. Silver. That's on the bad list. When you combine silver with a halogen, whether it's chlorine, bromine, or iodine, it's going to be insoluble. Lead 2 iodide, same thing. It's on the bad list. Double replacement or neutralization. Let's identify what we have here. We've got some kind of an acid because it starts with an H and it's got AQ. we've got a metal plus OH. That's a base. We're making some kind of ternary ionic compound, which happens to be a solid, and water. Does that sound like a double replacement or neutralization reaction? We said neutralization needs water, and that's what we see here. So this must be a neutralization reaction. You will need to be able to do all of these things for your homework and for the exam. I'm giving you practice that's similar to what you'll see. As always, we'll do more practice in class. So here's the recap. We've got combination reactions, decomposition reactions, single replacement, double replacement, neutralization. Watch live lecture for the cheat sheet. Or you can just come to class. You don't have to just watch it on YouTube. But if somebody's watching that's not in my class, watch the live lecture. Get the cheat sheet. So there's the carrot on the stick for you. We'll fill this out as a recap, and you can keep it in your notes. Okay. Diatomic molecules. You're going to need to know these, especially when you're writing out those chemical equations and writing the chemical equations as written descriptions. All of these molecules are written as 2-atom molecules when they're in a chemical reaction. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All of these are diatomic molecules. Hydrogen is kind of a loner. It's on its own. But all the others form a 7 in the periodic table. Starting with nitrogen, going over to fluorine, and all the way down to, let me try that again, because I included one that shouldn't be included, down to iodine. Forms a 7. Know these. Commit them to memory. Here's the list for you. All of that, we're leading up to balancing chemical equations. Not that difficult. I'll help you walk through some rules, then we'll do a few together, and we can do more in class, of course. But you have to come to class for us to do them together. When we write a chemical equation, the number of atoms of each element must be the same on both sides of the arrow. That's the goal. That's considered balanced. The way that you balance each element is by putting whole number coefficients in front of the substances that you need more of. I'm going to highlight whole number. We need whole numbers here. A coefficient is just a multiplier. And you'll remember that hopefully again from chapter 3 when we were looking at counting how many atoms were in a particular compound. If I have 3 H2O molecules, then that means I've got 6 hydrogen atoms and 3 oxygen atoms, because I'm taking 3 times the 2, the subscript for the hydrogen, is equal to 6 hydrogens, and then 3 times 1 is 3 oxygens. Remember, if there's no subscript, that means it's 1. So let's do a quick review of that. How many atoms of each element are present in the following compounds? Take a second, try it out. then rejoin me. So we've got hydrogens. There's a hydrogen here and here. So there's 4 hydrogens in one of these compounds, and this is acetic acid. And we've got 2 of this. So there's 8 hydrogens there. For the carbons, we've got 2 carbons in acetic acid, and there's 2 of these whole acetic acid molecules. So we have 4 carbons. Same thing with the oxygens. There's 2 oxygens in one of them. We've got 2, so there's 4 oxygens. Make sure that O doesn't look like a 0. H2, we've just got 2 hydrogen atoms. That's it. So that's a quick refresher on counting the number of atoms in each element. Before you put coefficients in an equation, make sure the formulas are correct. You may have an instance where you need to take the written description and write it as a chemical equation and then balance that chemical equation. If that's the case, double check your work and make sure that the formulas you've written are correct. You also never want to change the subscripts in a chemical formula. Let's make sure that we understand the difference. That 2 in front is a coefficient. Change at will. You're going to change that to balance the equation. However, that little 2 is a subscript. No touch, as I say to my children. No touch when they're very little. Keep it simple. No touch. Don't touch it. Don't change it. Because if you change that, you don't have water anymore. Leave it alone. Let it live. May be tempting. May seem like the easy way out. Don't do it. Leave the subscripts alone. They're bad for you. When you're balancing an equation, you want to start with the most complex formula. So usually something that's got, 3 elements in it or something like that, like calcium carbonate, or calcium phosphate. A lot of elements there. If, however, all of those elements appear on the same as a single unit, the polyatomic ions, then you can just balance it on both sides like a single unit. And I'll show you what that looks like when we do some examples of balancing. The coefficients have to be whole numbers. So if you have a fraction in there, then you need to get it out of there by multiplying by the denominator to get whole numbers. The denominator is the bottom number, so that's a 2. You'll multiply everything by 2. So you get 2 hydrogen gases, 1 oxygen gas, which you don't have to write the 1, and 2 liquid waters. So don't, if you use a fraction, fine, but don't leave it that way. The final balanced equation must have whole numbers. After you balance, make sure that you have the same number of atoms of each element or the same number of polyatomic ions on both sides of the equation. And for that, I like to do a little chart. The elements that we have are hydrogen and oxygen. We've got reactants. I just use an R. Products. I use a P. Then I go through and I count how many of each atom or ion I have. We've got 2 times 2 equals 4 atoms of hydrogen in the reactant side. And we've got 2 oxygen atoms. Product side, we've got 2 times 2 equals 4. And 2 times 1 equals 2. So we've got the same number of atoms on each side. That's how I like to check my work. Last check. Make sure that you have the smallest whole number ratio. I'm going to circle it and I'm going to highlight it. And I'm going to put some little marks around it. And I know you're probably like, okay, she's doing the most. But the reason is, when you're balancing chemical equation, you might be so excited. Oh my goodness, I finished it. It makes sense. It all checks out. But it's not the smallest. And that means it's wrong. So if I looked at this equation here, 2 hydrogens and 2 bromines, 4 HBr. Yeah, okay, it all checks out. It's the same number of atoms on each side. But I can reduce this, 2 and 2 and 4. That would be wrong. This is correct. Make sure that you have the smallest whole number ratios. Now let's try it. I'll show you how I do it. This is the guess and check method. There's no real formula for how to balance equations. It's just guessing and checking and practice. I start by making a table to keep track of how many of each atom, each element I have, or ion if there's ions. Here we've got iron and we've got chlorine. Those are the 2 elements that we see. And with no coefficients, I've got 1 atom of iron and 2 atoms of chlorine on the reactant side. Product side, still have 1 of the iron, but I've got 3 chlorines. That ain't balanced. So what you need to do is figure out the lowest common denominator. So what's the smallest number that both 2 and 3 can be used to divide evenly into? That would be 6. On the reactant side, I can multiply by 3. On the product side, by 2. Notice how I placed the numbers in front of the compounds, and I did not touch the subscripts. But now that I've done that, I've changed the number of irons that I have. So that was our first table. We did something. Now I make another table. Reactant side, we haven't touched the iron, so there's still 1. With the chlorine, though, there are now 6. It's 3 times 2 equals 6. Product side, we put a 2 in front of the iron 3 chloride. So now we've got 2 times 1, which gives us 2 iron atoms, and 2 times 3, which gives us 6 chlorine atoms. So the chlorine is balanced. The iron is not. We need the lowest common denominator for 1 and 2. That's going to be 2. You multiply the reactant side, the iron, by 2. Then we do our third box. This should be our last one because it looks like everything should be balanced. I've got 2 times 1, which gives me 2 of the irons. I've got 3 times 2, which gives me 6 of the chlorines. 2 times 1 for the irons on the product side. 2 times 3 for the chlorine. Now we're balanced. I have all whole numbers. And I can't reduce these anymore. 2, 3, 2. That's it. I can't divide them by something and get anything smaller that's still a whole number. Let's do one with some polyatomic ions. You check and make sure that these ions are still intact on both sides. So here's my sulfate ion, SO4, and it's intact. SO4 there. There's my nitrate and my nitrate. I see it all together on each side, so I can keep them together when I make my chart. Aluminum, sulfate, barium, and nitrate. For this first one, we're just taking a lay of the land. How many of each are we starting with? And do we have to balance at all? Because you might get that curveball of, hey, there's already the right number of each thing on each side, and I'm done. So we're starting with 2 aluminums because of that subscript there. We've got 3 sulfates. Remember to look at the subscripts. Barium, there's only 1. Nitrate, we've got 2. Product side, 1 aluminum, 3 nitrates, 1 barium, 1 sulfate. So it seems like some things have disappeared. We've got to do some changing and fixing to balance out all of these elements and ions. We've got 2 on one side and 3 on the other for nitrate. That's a little bit complicated. So let's start there. Lowest common denominator here is going to be 6. You find the compound on the product side that has nitrate, and you write a 3 in front of it. Did not change the subscript. I put a coefficient in front. Same thing on the product side. You find nitrate and you put a 3 in front. Or sorry, a 2. Did not change a subscript. I put a coefficient in front of the whole compound. And that's going to affect everything else. Making my second table. And now we get to work. We haven't touched this first compound, so there's still 2 aluminums, 3 sulfates on the reactant side. But we added that coefficient in front of the barium nitrate. So now we've got 3 bariums and 3 times 2 nitrates, which gives us 6. Product side, we've got a 2 in front of the aluminum nitrate. So we've got 2 times 1 gives us 2 aluminums. And 2 times 3 gives us, 6 nitrates. Make sure you write it in the right category, y'all. It's very easy to just write it all in a row. But that's why you got to pay attention to detail and check your work. We haven't changed the barium or the sulfate on the product side. So there's 1 and 1. So right now, we have our aluminum balanced and our nitrates balanced. But the sulfates, not so much. Barium, not so much. Luckily, we have the same situation, a 3 and a 1. So our lowest common denominator is going to be 3. So you multiply by 3 on the product side. And the barium and the sulfate are in the same compound on the product side. Place a 3 in front. We make our last table. So that was table 2. We're now going to make our farewell table. At least we hope it's the farewell table. So we've got 2 aluminums, 3 sulfates on the reactant side. We haven't put a coefficient in front at all. For the barium nitrate, we've now got 3 times 1 gives us 3. And we've got 3 times 2 gives us 6 for the nitrates. On the product side, we've got 2 times 1 aluminums gives us 2, and 2 times 3 nitrates gives us 6. My hand just has a mind of its own today, y'all. We've got 3 times 1 for our barium sulfate. And we've got 3 times 1 for our sulfate ion. So 3 and 3, sulfate and barium. It looks like everything checks out. So make sure that your numbers in the reactant column are the same as the products column. If this is true, then you're good to go. We're all balanced. Now, if this were a multiple choice question, or you had to give all of the coefficients for these in order, then your coefficients would be 1 which is what's the first one. 3, 2, and 3. Watch for that. If you need to give the coefficient, make sure that if there's no number in front that you say it's 1. Thanks for watching. We'll do more practice of balancing equations in live lecture, so make sure you come to that. We do practice problems. I give you test taking tips, tell you about assignments and exams, due dates, all that good stuff. So make sure that you watch. If you have questions, feel free to ask. Until then, stay safe.